All right, so we ended the last video with this example with theoretical yield, actual yield, and percent yield. I think I'm going to work through a couple more problems, just practicing the setup for the theoretical yield problems. Then we'll go on to the last topic for this set of slides. So I'm just going to make up a couple problems and we'll work through them together real quickly. So let's see, I have this equation 2H2 plus O2 makes 2H2O, and let's just say how many grams of H2O from 25.0 grams of oxygen. So here's my starting amount that I've got to work with, and I'm being asked to figure out the grams of water. So I'll need my molar mass for both O2 and water, right? 1 mole of O2, that's 16.00 for each oxygen, so 32.00 grams, and then 1 mole of H2O, that's 16.00 for the oxygen and 1.01 for each of the hydrogens. So to 2 decimal places, that's 18.02 grams. Other than that, all I need to know is the mole ratio in the balanced equation, which says 1 mole of O2 in, 2 moles of water out. So now we're pretty much ready to go. So the plan will be grams of O2 to moles of O2 to moles of H2O to grams of H2O. All right, so we can set that up. 25.0 grams oxygen, convert to moles, so times 1 mole O2 divided by 32.00 grams O2. So grams of reactant cancel, and that's my first conversion. Then balanced equation says for 1 mole of O2 in, I get 2 moles of water out. Again, I'll box this just because this is the only piece of information coming from the balanced equation. Moles of reactant cancel, so that's our second step. And then in our last step, 1 mole of water is 18.02 grams of water. So moles of product cancel. We're left with grams of product. That looks good. That's our third conversion. Let's see what we actually get for our answer. To 3 significant figures, I got 28.2 grams of H2O. So again, remember in this problem, we talked about the amount of O2, but we assume there's the appropriate amount of H2 to react with it. So it's not surprising that 25 grams of O2 made 28.2 grams of water, because we're also combining hydrogen in as well. Okay, let's do one more of these just so you can see. I thought a couple more examples from scratch would be helpful, so let's do one more of these. Okay, this time let's say my equation is N2 plus 3H2 makes 2 NH3. And let's say our question is how many grams of NH3 from let's say 15.0 grams H2. All right, so my reactant amount, H2, here it is in the equation. Then my product question is about grams of NH3, which happens to be the only product in this case, so that's what we've got there. We need our molar masses to start out with, right? 1 mole of H2, that's 1.01 each, so just 2.02 grams. And then 1 mole of NH3, that's 14.01 plus 3 times 1.01, so that's 17.04 grams. And then the only other thing, right, our balanced equation says 3 moles of H2 in, 2 moles of NH3 out. So our plan, grams of H2 to moles of H2 to moles of NH3 to grams of NH3. All right, so we have what we need to do that. So 15.0 grams H2 times 1 mole H2 over 2.02 grams H2. Grams cancel, that's our first step. Then just say whatever the balanced equation says, which is 3 moles of H2 in, 2 moles of NH3 out. Again, boxing this step, that's the only one coming from the coefficients in the equation. Verifying that we're still on the right track, converted moles of reactant to moles of product. And then in the last step, moles of product to grams of product. So 1 mole NH3, we see that's 17.04 grams NH3. Correct cancellation. Now we're ending up in the units we want, grams of NH3. Let's see what we get here. 84.4 grams NH3. So again, that number is way bigger than the grams of H2 we started with, but that's totally okay because we can't forget we're also combining in N2, whatever amount it is we would need to fully react with the H2. N2 is a lot heavier than H2, so it's not surprising that this number is so much bigger. Okay, so I thought it might be helpful to look at a couple more of those before we went on back to the slides. So we'll go back to the slides now. So this last topic that we're going to consider is called limiting reactants. And these problems are going to be pretty similar to theoretical yield problems. They're kind of going to be like double theoretical yield problems. But essentially the principle here is you're going to be given a reactant amount for both reactants. Then effectively our goal is to figure out which one is going to run out first. And at the point that it runs out, how much product do we expect to have for? So I have kind of a silly analogy just to help you think about kind of what we're considering here. And I kind of mentioned earlier thinking about a balanced equation as a recipe, so we'll sort of do that here. So basically gathered our ingredients for some cookie recipe, whatever it may be, butter, sugar, flour, eggs, and the intention here is for you to see that we're low on sugar, so we can, generally we'd say we could make cookies until we run out of one of the ingredients, and then in this case we're saying sugar is what we're going to run out of first, and once we run out of that we won't be able to make any more cookies. So in principle that's the idea with limiting reactant, that the balanced equation is my recipe. I'm given the relative amounts of each component, figure out which one is going to run out first, and then with that information, figure out the maximum amount of of product that I'm able to make. Okay, so here's my weird recipe for cookies, but 9 cups of flour, 3 cups of sugar, and 3 eggs to make 108 cookies. And so then in the first question here, I just said, how many cookies can we make if we only have 1 cup of sugar? So we needed 3, but we only have 1. So we can make 1/3 of what we would theoretically be able to make according to the recipe. So that would be 108 divided by 3, right? And that should be 36 cookies. And then in the next question it says, well, what if I only have 2 cups of sugar? Then what's going to happen? Well, then that's 2/3 of the amount that the recipe calls for. So I'll only be able to make 2/3 of what it says, which is, I guess, double our last answer. So that should be 72 cookies. Okay, so my weird recipe, I just wanted it divisible by 3, but fair enough. That's what we have there. So that's just the concept, right? Identify what's going to run out first and then figure out how that's going to restrict the amount of product we're able to make. So in terms of terminology, we would say that the sugar is the limiting reactant because it limits the number of cookies you can make. So relative to the balanced chemical equation, whatever runs out first, that's going to be what we describe as the limiting reactant. And on the other side, whatever we have extra of, we'll see that's called the excess reactant. Okay, so now we'll leave the cookie world behind and think about a chemical reaction instead. So here we're revisiting 2H2 plus O2 makes 2H2O, and it's telling us we start with a combination of 10 hydrogen molecules and 7 oxygen molecules, and we want to know what's going to happen. Well, the reaction is a 2-to-1 reaction, right? 2 hydrogens are going to react with 1 oxygen. So in this case, I have 10 hydrogens, but I've got 7 oxygens. And these are in molecules, but they could just as well be in moles. So I have more oxygen than I need, which means that hydrogen is the limiting reactant. So based on the balanced equation, it should make sense that I make 10 water molecules, right? It's a 1-to-1 ratio between H2 and H2O, or a 2-to-2 ratio. That consumes 5 oxygens, but that means that 2 of them are left. Looks like here's one and here's the other, and then the rest got converted into water. So we'd say hydrogen is the limiting reactant and oxygen is the excess reactant, but when I run out of the limiting reactant, I have 10 waters that I've formed. So then hydrogen would be the limiting reactant and oxygen would be the excess reactant, reagent. We can use those terms interchangeably, would be the excess one. So what do I do in practice to deal with a limiting reactant problem? Well, the first thing I need to do is correctly identify it as a limiting reactant type problem. And that's pretty straightforward because now all of a sudden I'm going to be told about reactant amounts for both reactants, for more than one reactant. The question will still be the same. It's going to ask us about the amount of a particular product that's going to form, but I'm given both reactants. So there are a lot of strategies we can use to calculate the yield in a limiting reactant problem. My preferred strategy, and it seems that students like this better than the other strategies I've previously proposed, is simply to say, just do the theoretical yield calculation first for the first reactant, and then again for the second reactant. Whichever one of those calculations gives you the lower product amount, that will tell us not only which reactant is the limiting reactant, but it'll also tell us the amount of product that we're going to make. So I'll run this calculation twice. Whichever one gives me the lower theoretical yield is the limiting reactant, and that lower theoretical yield that we calculate is the actual answer to the question. Okay, so here we kind of followed standard protocol, right? With sodium carbonate, we went grams of sodium carbonate to moles of sodium carbonate, using the balanced equation to go to moles of sodium chloride, and then lastly to go to grams of sodium chloride. So just following along, right? Grams of reactant divided by its molar mass, so grams cancel grams. Then here's moles of reactant, and now moles of reactant shows up in the denominator as we go from the reactant side to the product side. Remember, I've been boxing this step just to indicate that's all that's coming from the balanced equation. And then in the last conversion, right, going from moles of product to grams of product. So everything cancels in a pretty logical way, and we're left with grams of sodium chloride, which is what the question is asking us. If we do that calculation, we get 13.8 grams of sodium chloride. For the moment, that doesn't tell me anything, right? That just tells me 12.5 grams of sodium carbonate will lead to 13.8 grams of sodium chloride. So now I need to do the same thing with the other reactant. So we'll do that on the next page. So now we're using our 16.8 grams of calcium chloride. Okay, so same plan, grams of reactant to moles of reactant to moles of product to grams of product. We can verify that this cancels out as before. Grams of reactant cancels with grams of reactant, moles of reactant with moles of reactant. Again, here's my conversion factor, 1 mole of reactant in, 2 moles of product out, and then moles of product cancel with moles of product. The units we're left with are the correct units. When we do this calculation, we get 17.7 grams of sodium chloride. So now we know 16.8 grams calcium chloride gives 17.7 grams sodium chloride. So the previous number was the smaller number, right? 13.8 grams came from the sodium carbonate versus 17.7 from the sodium chloride. So I don't add these together, right? This was just a quick way to evaluate the amount I would get from either initial reactant amount, and whichever one of those values is smaller, that's going to be my answer to the problem. So I kind of went through this down below here. What does this tell us? Well, since we got a smaller number from the theoretical yield calculation for sodium carbonate, it must be the limiting reactant. And when it runs out, we end up with 13.8 grams of sodium chloride. So again, there are a lot of ways to do this type of problem. This is what I've found that students like the best as a method to solve it, because you're comfortable doing the theoretical yield calculation. So you just do that twice, and whichever number is smaller, that's your answer to the problem. And this makes it easy to account for any coefficients anywhere in the balanced equation. It's a pretty straightforward approach to doing these. If you learned it differently before when you took chemistry, totally fine, whatever method you feel confident with. My experience has just been that students prefer this method because it's a straightforward approach, just kind of a double theoretical yield problem. Okay, I think I have one more of these for us to work on, and that's pretty much it for this video. Okay, same equation, different numbers essentially. So it's saying, again, 14.2 grams of sodium carbonate, 13.6 grams of calcium chloride, and the question is still how many grams of sodium chloride would be produced. So really all I need to do is kind of follow the examples from the previous two, run the theoretical yield calculation twice. My smaller number is my correct answer. So 14.2 grams sodium carbonate convert that into moles of sodium carbonate. I think that's 105.99. Yes. 105.99 grams sodium carbonate. It's 2 sodium chlorides for every 1 sodium carbonate, so 1 mole Na2CO3, 2 mole NaCl, and then reporting my answer in grams, 1 mole NaCl, 58.44 grams NaCl. Just because we keep using these numbers, I've just copied them from before, but we can figure them out. Grams of reactant goes with grams of reactant, moles of reactant goes with moles of reactant, moles of product goes with moles of product. Left with my correct units of grams of product. Let's calculate that. Uh, 15.7 grams sodium chloride. Okay, I don't have anything to do with that number yet, right? I need to calculate it for the other reactant before we can really go any farther. So 13.6 grams calcium chloride times 1 mole calcium chloride. We could calculate it, but it's just right here, right? 110.98 grams calcium chloride. Same ratio, right? 1 mole CaCl2 in, 2 moles NaCl out. Oh, I guess I've been boxing this and I forgot. Up there, we'll do it here. And then the last step's going to be identical, right? 58.44 grams sodium chloride per 1 mole. Things cancel out correctly. Grams with reactant, moles of reactant, moles of product, left with grams of product. 13.6 divided by 110.98 times 2 times 58.44. That gives me 14.3 grams NaCl. So what does this tell me? What do I want to conclude out of this? I would say calcium chloride is the limiting reactant. And when it runs out, 14.3 grams of sodium chloride is formed. So this is my answer to the question, 14.3 grams of sodium chloride. So again, this is my preferred way to do these problems because it's very direct. You just run the calculation twice and the lower number is your answer. So once you identify that it's a limiting reactant problem, then this would be the approach I would recommend. If you're looking it up in a different book or watching another video and they show you a different way that you like better, totally okay. I think this way works great, but there are certainly other ways to do it as well. Okay, I think that's it. This is just one more, okay. So one more practice, kind of the same idea here. 20 grams of N2, 4 grams of H2. The question is, how many grams of NH3? Okay, so pretty straightforward here. So here's our 20 grams of N2, 4 grams of H2. We'll do our theoretical yield calculation each time. Don't forget about the coefficients, right? There are 3 and 2 there, plus obviously a 1 out there, so don't forget about those. Okay, so 20 grams of N2, 1 mole of N2, It's 14.01 each, so 28.02 grams of N2. For N2, the balanced equation says 1 mole N2 in, 2 moles NH3 out. And then for 1 mole NH3, it's 14.01 plus 3.03, so 17.04 grams NH3. Verify that things cancel appropriately. Grams of reactant, moles of reactant, moles of reactant, moles of product, moles of product. There's my correct units. Let's see what we get here. .3 grams of NH3. Okay, so we'll repeat the same process for the other reactant. And this way is convenient because it's going to deal with the coefficients in the balanced equation. Okay, 1 mole H2. That's 1.01 for each of them, so 2.02 grams H2 times, from the balanced equation, it says 3 moles H2 in, 2 moles NH3 out. And then the last step's the same, right? Converting from moles of product to grams of product. 17.04 grams NH3. Okay. Grams of reactant, moles of reactant, moles of reactant, moles of product, grams of product is left. .5 grams of NH3. So then in this case, I guess we would say H2 is limiting, 22.5 grams NH3 formed. Okay, so I hope this method is making okay sense to you after seeing a few examples. Again, like I said, if there's another method you prefer, that's totally okay, but hopefully this is making reasonable sense. Okay, so I think I'll end this here. This is the end of this set of chapter 3 and 4 slides. So in the next video, we'll start in on the second half of these slides, which is talking more about solution chemistry.